In this module we will discuss about AC voltage controller. AC voltage controller. What is that AC voltage controller means? Here output load, how much it is expecting that AC supply, no? According to that will supply the AC voltage to the load. We will see what is the definition of this AC voltage controller, how this AC output voltage can be controlled. We will see that. Most of the loads need variable or regulated AC power. So you no need to require complete AC power, you require just some of the variable or regulated AC supply. For example, motor, heating furnace. Motor means according to motor speed you need to supply AC voltage. If you want to rotate that motor with high speed, you should supply high AC voltage. If you want to make that motor to rotate with a low speed, you should supply less AC voltage. Next, heating furnace. If you are having heater, then you can increase the temperature of the heater or you can decrease that using heating furnace. Next, you can have blower, pumps, lights, etc. Then AC voltage controller are used to drive such loads. AC voltage controller consisting of SCR as a switch. You have SCR, circuit controlled rectifier. We are using this one as a switch in AC voltage controller. It normally takes main supply as an input and provides variable AC to the load. SCR are used to control the RMS value of the load voltage. Means according to our load requirement, we will make this SCR on and off. Using this SCR, we are controlling the load voltage. If input AC is variating, then same application need regulated AC. The AC voltage controller are also used in such applications. Then they are called as AC voltage regulator. AC voltage controller use either on and off control. Actually here there are two types are there in AC voltage controller. They can use on and off controller, or it is phase angle control to transfer required power to the load. Here you can have a circuit diagram of AC voltage controller. Input is main supply, output is load. Next we will see in on and off control, SCR conducts fully for a few cycles and they are fully off for another some few cycles. We will see that why it is called as on and off cycle. We will see next circuit diagram of on and off circuit. This is the circuit of on and off control. Here you have the main supply. Here you have anti-parallel SCRs. Here you have connected SCR in anti-parallel fashion. Next you have the load. According to your load requirement, you will make your SCR on and off. So this is the circuit diagram of single phase full wave controller for on and off control. So we will see this circuit diagram. We are supplying sinusoidal signal for this circuit. We will make SCR1 in this interval. SCR1 on in this interval. Means this is the gate drive of T1. Means you are applying IGT1. From this one you are making your SCR on. Next you are making second SCR on using this one. Means this pulse, first T1 pulse, it will make this SCR on and it will conduct during positive cycle. Here you can see during this positive cycle it will conduct. In negative cycle you need to make T1 on. So in negative cycle, how current flows from supply to load back again to T2, T2 to supply. Like this it will conduct. That will be conducted with help of the T2 pulse. So negative cycle will be conducted using this T2 pulse. Similarly, positive pulse will be controlled by this positive waveform. Next, during negative cycle, you require another pulse like this. it will be on for n cycle. Next it will be off for another m cycle. You can see this is the output voltage V0. So you can call this one as a on and off circuit diagram. So you can see this is the on and off controller circuit diagram. It is on for n cycle, it is off for m cycle. This is the waveform of on and off type AC voltage controller. You see what they have written. Here in sometimes they will use a triac instead of using anti-parallel. Usually you know that what is the meaning of triac. This is the triode for alternative current, and also in triac what you have, anti-parallel ACR. So you will use this triac to conduct this. So next we'll calculate the voltage and all for this. Before that we'll see what are the advantage we'll get and what are the disadvantage we'll get. ACR are switched on at zero crossing, as we have seen. ACR will be on during zero crossing because you have applied IGT1 at a zeroth instant only. Hence harmonics due to switching action are reduced here, because immediately ACR get turns off. This is the advantage. Here, and the disadvantage is what? Full supply voltage is applied across the load during on period, and load voltage is 0 during off period. Hence load voltage is not a smooth, rather it is intermediate, because you are making that one on completely during the off period. So it is not a smooth waveform here. Load has sustained these variations. Sometimes you may get a maximum voltage, sometimes load may get a 0 voltage like this. No, you can have some voltage fluctuations like this. So this load has to maintain this voltage fluctuations. So next we will see one of the simple derivation for this. Obtain an expression for RMS value of load voltage in on and off AC voltage controller. Here you can have the supply voltage is Vs equal to Vm sin omega t. This is your supply. Next we will get V0 RMS. V0 RMS equal to 1 by t 0 to t Vs square omega t d omega t whole raised to 1 by 2. And we have seen total T period means it includes on period plus off period. It includes n cycle plus m cycle. It will be on for some cycle and it will be off for another some cycle. It will be on for n cycle and off for m cycle. So you can see, so you can represent this total T period as n divided by n plus m, and you should substitute actually T means total cycle, no? What is your total cycle? 360 degree. So that is 1 divided by 2 pi. Pi means it is 180, 2 pi means it is 360. So total T period includes 360 degree, and this T means what? 2 pi. Next Vs you can substitute to Vm sin omega t into d omega t whole raised to 1 by 2. And also in this case take this 2 pi outside. Next Vm is constant, keep it outside. Next remaining is sin square omega t into d omega t. And also in this case you know that it will be on for n cycle and off for m cycle. So as you have seen this waveform, it will be on for n cycle and off for n cycle. So we'll consider this part n into n divided by m plus n. This is what? This is the duty cycle. It is represented by the parameter k. This is the duty cycle. So it is represented by n divided by n plus m. Hence what I do, I will multiply this parameter by this duty cycle n divided by n plus m. So next, how can write down the sin square omega t? you can write down this one as 1 minus cos 2 omega t divided by 2. Sin square omega t can be written as 1 minus cos 2 omega t divided by 2. And in this case, you can take 1 by 2 outside. You kept that 1 by 2 outside. Next, constant is 1. Next, cos 2 omega t divided by 2. This is here. After simplifying this and after substituting these limits, we will get the simplified things. Then after simplifying, finally we will get Vm by root 2 root n divided by n plus m, where n divided by n plus represents n plus m represents duty cycle of on and off control. Hence above equations become V naught Rm is equal to Vm by root k, V naught Rm is equal to Vm by root k. Vm by root 2 into root k, you will get this. Next, Vm by root 2 is nothing but Vs Rms. So you can rearrange this one and you can write down this one as V naught Rm is equal to Vs Rms into root k. Next, we will go with one simple problem. In an on and off control circuit using a single phase 230 volt 50 Hz supply, the on time is 10 cycle and off time is 4 cycle. Calculate the RMS value of the output voltage. For this one, now first I will write down what are the given parameters are there. They have given input supply, that is of 230 volt. Here I have written Vs equal to 230 volt and it is on for n cycles, so you will get n equal to 10. It is off cycle is of m equal to 4, so you can write down the duty cycle as k equal to n divided by n plus m. So after simplifying this one, you will get the duty cycle as 10 divided by 14. From the equation, RMS value of the output voltage is given by V naught RMS equal to Vs RMS into root k. Next, you can write down V naught RMS equal to Vs RMS is how much? 230. Root k is root 10 divided by 14. You will get V naught RMS as 194.38 volts. Next, we will go with another one simple problem. Similar to this one, how we have solved now, we can use that formula and we can solve that. They have given the input parameter and you can use the above formulas and you can calculate the values. V naught RMS they have calculated, I naught RMS you can get from this V naught RMS. Next, I naught active load power P equal to I square into I. You know that from this one you can able to calculate I square as 360 watts. Next, IS RMS equal to I naught RMS, this is equal to 6 amp. Hence total RMS input power is total RMS power as P equal to input power. If you want to calculate the input power, you can calculate total RMS power as Vs into Is. Vs RMS into Is RMS, you will get this. You will get 720 volts per ampere. Next, power factor is equal to active load power divided by total RMS input power. So we will get this one as a 0.5 lagging. Next, to obtain RMS and average current of the thyristor, here no we have already got I naught RMS as a 6 amps, where I got this I naught RMS in nothing but IS RMS, so I got that one as a 6 amps. The RMS current of T1 is T1 trans. Actually here we have used two anti-parallel SCR. For SCR T1 it is IT1, for T2 it is IT2. So you can write down I naught RMS square equal to sum of IT1 square plus IT2 square. And also you know that IT1 and IT2 this is equal to IT. So you can write down this one as I naught RMS square equal to RMS square equal to IT1 square plus IT square plus IT square. You will get IT I naught RMS square divided by 2 equal to IT square. Next you will get IT equal to I naught RMS divided by root 2. You will get 4.24 amps. Next, if you want to calculate average thyristor current, can use this formula. You can calculate IT1 average equal to N by N plus M. So 1 divided by 2 pi 0 to pi I of t into dt. After simplifying this one, you get the expression for IT1 average. You can use this one and you can solve this one, and you will get value for IT average is 1.31, and average value of thyristor 1 and thyristor 2, these two are the same. Thyristor 1 and thyristor 2 represent, this is a SCR1 and SCR2, this is same. So we will get IT equal to IT1 equal to IT2, this is 1.35 amps. Thyristor current in on cycle will be this one. On for n cycle, it is off for n cycle. Next, we can solve another one problem. There also we have calculated power factor, total RMS we have calculated, and we have used all the formulas what we have discussed till now. From this one we will get power factor. Next, we have some university questions you may get from this section. What are the university questions you may get? Explain the principle of on and off control. Obtain an expression for RMS voltage, RMS current and power factor. So this is first question we will get from this section. With the help of circuit diagram, explain operation of single phase AC regulator using on and off control. Derive the expression for RMS value of load voltage. So next we have to list advantage and disadvantage for this on and off control. So these are the university questions you may get from this on and off control section. Next we have phase control. Principle of phase control. If you look at the circuit diagram, it is clear that instead of using anti-parallel SCR, we are using one SCR that is parallel with the other. This is a single phase half wave controlled, and this is a unidirectional controller. Here you can have main supply, that is Vs. This is provided with the Is, and we have connected one SCR, that is T1, and we have connected one parallel diode D1, and this is connected with a load. And if you look at this waveform, you can clearly observe that whenever you apply the pulse, it will get turns on. When it gets turns on, then only you will get the voltage across the output load. You will get voltage across. And also you know that during negative cycle, it will be conducted through diode. So diode will be conducted during negative half cycle. So you will get negative half cycle. This is D1. Similarly for T1 you can observe this is T1. Next, during D1 it will conduct that. This is the output voltage V0. Similarly, you can able to get output current I0 also. This is also similar to your output voltage V0. From this one you can able to calculate derivation for this. Derive an expression for RMS and average value of output voltage for single phase half wave controlled rectifier. Vs omega t equal to Vm sin omega t. Next, V0 RMS equal to, what is the standard formula I have? This one. So you can see that you have turned on this one in alpha period. So alpha to pi, pi to 2 pi, we will divide the interval of 0 to t as alpha to pi, pi to 2 pi. Next, in this case now, instead of in place of V0 you can substitute Vm square sin square omega t d omega t. Here also you can substitute this whole raised to 1 by 2. Next, you can take this Vm outside, so we will get Vm square divided by 2 pi. This is the constant. Fine. Next, sin square omega t, you can keep this one as sin square is nothing but 1 minus cos 2 omega t divided by 2. You get 1 minus cos 2 omega t divided by 2. And after simplifying this one, you will get V0 RMS as Vm by pi root of 2 pi minus alpha plus sin 2 alpha divided by 2 whole divided by pi. This is the derivation result for this one. You will get I naught RMS equal to V naught RMS divided by pi. Similarly, you can able to calculate V naught average at this one. V naught average equal to 1 by T0 to T V naught omega T into dt. After substituting this one and after simplifying this one, and we will get V naught average as Vm by 2 pi into cos alpha minus 1. So we have another one simple problem. So here you can look at this problem, and this problem is asked for sometimes it is asked for 10 marks, and in one question paper they have asked this one for 6 marks. We'll see what is that problem. A single phase half bridge AC voltage controller, this name itself explains which circuit you are using. The single phase has a resistance load of R equal to 5 ohm and input voltage Vs equal to 120 volt 60 hertz, and the delay angle of the resistor is alpha equal to 5 by 3. Determine, first one is what? RMS output voltage. Already we have derived the expression to calculate RMS output voltage. What is that formula? V naught RMS equal to Vm by 2 root of 2 pi minus alpha plus sin 2 alpha divided by 2 whole divided by pi. Similarly, input power. So you can able to calculate input power as P equal to Vi, you know that. So for that one, first you have to calculate I naught. From this one you can able to calculate that. Next you have to calculate average input current. I naught average you have to calculate. First we have to calculate V naught average. From this one you can calculate. So first I will write down the given parameter. So they have given input Vs as a 120 volt and R as a 5 ohm and alpha as a pi by 3. From this one you will get this active load power P equal to I square into R. You will get this active load power P equal to I square into R. You will get active load power as 2598.47 watts. Next you will get ISRMS as V I naught RMS at this one 22.79 amps. From this one you will get total RMS power as P equal to Vs RMS into Is RMS. You will get this. Actually here Vs RMS they have given is the problem, and Is RMS is nothing but this is equal to I naught RMS. Next power factor we can able to calculate. Active load power divided by total RMS input power. From this one you will get this. Next average input power V naught average equal to Vm by 2 pi cos alpha minus 1. You will get V naught average as minus 13.5. Average input current you will get. Next you will get I naught average equal to V naught average divided by R. You will get minus 2.7 amps. Similarly we have another one problem. There also we need to calculate the parameters shown in this one. We will see what are the university questions we needed from this section. Define duty cycle and delay angle of AC voltage controller. Explain the principle of phase controller. So explain the operation of single phase unidirectional AC voltage controller with the resistive load. Derive the expression for RMS output voltage. So whatever the concept we have discussed. Next we have single phase controller with the resistive load. Next concept. Single phase controller with the resistive load. Here this is the bidirectional controller. Just now we have seen unidirectional controller. There we have controlled only positive cycle. Negative cycle is not controlled because there we have used diode parallel with SCR. So now we will go with the bidirectional controller. You can see this single phase full wave bidirectional controller. This circuit looks similar to what on and off controller. You can just look at the waveform for that. But actually operation of this bidirectional controller is somewhat different. Actually in that on and off controller, what you did, you have done on for M cycle and off for on for n cycle and off for m cycle you have done there in on and off controller, but in this bidirectional controller what you did, this is somewhat different. What is that? Here output voltage will be controlled by applying gate drive of T2. Similarly, you have applied gate drive for T2, there also you have controlled another output voltage. Like this you have controlled both the positive cycle as well as negative cycle. So like this you will get the waveform. This is the output voltage we know. Next you can look at the voltage across SCR. Why you will get voltage? Actually here you can see that in this period what is the status of your SCR? SCR1. Here you can observe that there are two SCRs are there. Here you have SCR-T1, that is whether that is on for the cycle or off for the cycle, you should observe this. Actually it is off, so it is off. So whatever the supply you will connect, here you can observe that it will be conducting only in this cycle. In this cycle it will be off. So if it is off, whatever the supply you connect across this T1, no, that will get appears across T1. So that same thing happened. Supply is this one, so it will get appears, and we will make this one on at phase alpha. So whenever it start to conduct, obviously you know that resistance of this SCR which is in conduction state, no, that resistance will be 0, so voltage drop will be 0. You know that V equal to IR, so obviously R is 0 means V is also 0. But thing is that Ohm's law is not applicable. For just understanding purpose I am telling you. Obviously resistance get decreases here when it get conducts. Obviously voltage drop will take place. Next you can observe there is a flow of current across the load. Obviously this load is multiplied by the current you will get this way. Like this now you can see whenever T1 is conducting it will conduct, whenever T2 is conducting it will conduct like this. So next we have derivation for RMS value of output voltage of single phase controller. So there also we know RMS, whatever the procedure we have followed in previous derivation, or that same procedure we apply. We are applying that same procedure. There we have we are applying alpha to pi. Next it is on for pi plus alpha to 2 pi. You have to substitute these limit. Only in these derivations only limits get changes. As this limit get changes, now obviously output result waveform what you will get, now that also get changes. Next you can substitute V0 as Vm into sin omega t, Vm into sin omega t, and also you know that V0 will be Vs whenever HCR is conducting. So take Vm outside, so sin square is nothing but 1 minus cos 2 omega t divided by 2, 1 minus cos 2 omega t divided by 2. You get V0 RMS as Vm into root pi minus alpha plus sin 2 alpha divided by 2 whole divided by 2 pi. In above equation, whenever alpha equal to 0, when alpha equal to pi, whenever alpha equal to 0 will get V0 RMS equal to Vm by pi. So V0 RMS equal to Vs RMS, and alpha equal to pi means will get V0 RMS as a 0. So here you can observe that output can be controlled from 0 to Vs RMS by varying the firing angle. Here we have the firing angle. Now by varying that we can able to control on and off of this SCR. So by varying this firing angle from pi to 0, since output voltage, current and voltage as well, supply current and symmetric, hence you can able to control this. So we have some problem for this section. For single phase bidirectional controller, so that name itself explains which formula you should use. I have written the given parameter R equal to 10 ohm, Vs RMS equal to 230, firing angle alpha equal to 45 degree, that is pi by 4. Next, from the derivation I already got V0 RMS as Vm into root of pi minus alpha plus sin 2 alpha divided by 2. From this one I can able to substitute Vs equal to Vm by root 2, so you will get Vm equal to root 2 into Vs. From this one now you will get this one 325.26. V0 RMS you will get V naught RMS result as a 219.3 volts. Next you will get V naught equal to P equal to V square by R, so you will get 4.82 kilowatt. Similarly, you can solve another problem. So like this, they have solved n number of problems in this section. You can go with this. Next, we can have another section, other circuit configuration of a single phase full wave controller. Single phase full wave controller with common cathode section. So if you look at the waveform, you can clearly observe when it will conduct and when it will not conduct. You can clearly see that. So we'll see that waveform first. In first cycle, what you do? D1 conducts, T1 conducts, D2 conducts. Just look at your waveform, circuit diagram. Actually for this one they have not given the waveform, that is the waveform for other circuit. So here you can observe that during positive cycle you can make from supply to T1, T1 to D2, D2 to load back again to supply. So during negative half cycle you can observe that supply to load to T2, T2 to T2. Like this now you can able to control here. So here you can call this one as a single phase full wave controller with a common cathode. So here you can see gate cathode drive of 2 ACR must be isolated. Gate and cathode, that is isolated. Observe that cathode of T2 is connected to anode of T1. Hence gate as well as cathode of T1 and T2 must be isolated. Hence other circuit configuration are developed which eliminate the necessity of isolation. Single phase full wave controller having common cathode connections of the ACR. You can see that. Cathode of ACR T1 and T2 are connected together. T1 and T2 cathode is connected here. This is anode and this is cathode. This is anode and this is cathode. This cathode and this cathode is connected, so it is called as a common cathode. So in a positive half cycle of the supply, T1 diode D1 conducts. In negative half cycle you can observe that T2 and D2 conducts. In this circuit, gate cathode drive need not be isolated, but isolation is normally provided between the control and power circuit. 4 devices are required in above circuit. Efficiency of the circuit is slightly reduced due to increasing power dissipation in the device. The waveform of the circuit is similar to that is shown in this circuit. Next we'll go with the next section. Single phase full wave controller with one ACR. Here you can see that one ACR. By looking at this one, you can observe how it gets conducts from supply to D1, D1 to T1, T1 to D2, D2 to load. It will get conducts during positive half cycle. During negative half cycle, how it gets conducts supply to load, load to D3, D3 T1, T1 to D4. Like this now it will get conduct during negative half cycle. So this is your main supply. Next gate, whenever you will apply a gate, your ACR gate conducts, and you should observe that both positive cycle and negative cycle current will flow through this T1 ACR only. So because of this gate drive of ACR T1 needs this one, these are the gate drive. So output voltage V0 will be like this. So during positive cycle you will get this. During negative cycle you can see. So you can observe that both positive cycle and negative cycle waveforms are controlled using this only one SCR. So you can observe how it will be conducted during positive cycle. So you can observe all these things. During negative half cycle, how it will be conducted. So you can see that how it will be triggered. You can observe that output voltage is this one. This is the waveform of the single phase full wave controller with one SCR and rectifier bridge. This is the concept. So we have some advantage. Input and output current and voltage are symmetric, as we have seen. There is no DC component. Transformer and motor saturation problems are absent. It is used in full wave controller are used for induction motor and function some of the fans it is used. So because you are controlling in fan in both cycles, you want to apply the voltage. So we'll see what are the university questions you may get from this section. With help of neat circuit diagram and waveform, explain the operation of bidirectional controller with R load. Explain the operation of single phase bidirectional controller with resistor load, and obtain the expression. So we'll get this type of concept. Next one is single phase controller with inductive load. We'll see this concept in next session. Thank you.